All right, here are the solutions to week 7, unit 4, lessons 1 and 3. So unit 4, number 1 here, lesson 1, number 1 says select all sequences that could be geometric. Remember, if it's a geometric sequence, that's indicating multiplication from one term to the next. So 2 to 4 would be a multiplication of 2, but then 4 to 7 would not. So this is not geometric. Letter B, 1/3 to 1 would be multiplied by 3. Then from 1 to 3, we would multiply by 3 again, and 3 to 9. This could be a geometric sequence by the looks of it. Letter C is going up by 2 each time, not multiplied by 2, just adding, so that's arithmetic. Letter D, however, is multiplied by 4 each time. 1/2 times 4 gives you 2. 2 times 4 gives you 8. 8 times 4 is 32, and so on. For letter E, we could, looks like we're dividing by 5 there from term 1 to term 2. So if that pattern stays the same, yep, that's geometric also. But letter F is not. We're just subtracting 100 each time there. So number 1 answers B, D, and E. I'll make that all our geometric sequence, or could be. Number 2, a blogger had 400 subscribers to her blog in January. The number of subscribers has grown by a factor of 1.5 each month. And so we want to write a sequence to represent the number of subscribers in the 3 months that followed. So 400 is the 0th month, maybe, think about it that way. And then we want to know the 1, 2, and 3 months. So 1.5 times 4 would be 600. 400 would be 600. 600 times 1.5 would be 900. And 900 times 1.5 would be 1,350. So those would be the first 3 months following the original month. Or following January, I guess. Tyler says that the sequence 1, 1, 1 of repeating ones is not exponential because it does not change. Do you agree with Tyler? I disagree. No. So I do not. And the reason is because although it doesn't change, it could be seen as multiplication by 1. So, it's not a very interesting sequence, but it could be a geometric sequence with a factor of 1. Number 4, in 2000, an invasive plant species covered 0.2% of an island. For the 5 years that followed, the area covered by the plant tripled every year. A student said that means that about half of the island's area was covered by the plant in 2005. And so let's take a look at it. If it's 0.2% originally and our growth factor is 3, and that's happening every year, so our t is in years, we could call this g of t. And let's see, let's put a 5 in there. So I'm going to take this over to Desmos, and we'll put our function in here. It started at 0.2, and we're going to multiply that by 3 to the x power. And actually, let's just put a 5 in there because we want to know after 5 years. So yeah, about 48.6% then in 5 years. So I would agree with that student there. Number 5, a square picture with side length 30 is scaled by 60% on a photocopier. The copy is then scaled by 60% again. So what's the side length of the second copy of the picture? So we start at 30, we multiply it by 0.60, and we do that again, or 0.60 to the second. And so we can do that on our Desmos calculator. We start with 30, multiply by 0.60 twice, and so we get 10.8 10.8 centimeters. And then letter B asks, what is the side length of the picture after it has been successfully scaled 60% 4 times? So I'm just going to do this to the 4th power then. And so we'll go over here and just change our 2 to a 4. And our size, the size of the picture is 3.8 repeating, so, or 3.888. So that's it on that one, and this is centimeters also. A geometric sequence starts, a G starts at 5, then goes to 15, and so on. Explain how you would calculate the value of the 50th term. So this is back from Unit 1 when we first started talking about exponential growth. And so if we would consider the 5 our first term and the 15 our second term, we could write our geometric sequence as g of x is equal to 5 times, it's our growth factor is 3, and if 5 is our first time, we'd have to do an x minus 1 up here if this is our first term, because then 1 minus 1 would be 0, 3 to the 0 is 1, and we do get 5. So that's one way of writing it. And then how would you get the 50th term? Well, then you would just put 50 in here, and so you would get 49 there. So, and I'm not going to do that. That's a pretty big number, but I think they just asked how would you do it, so we're good. Number 7, select all the expressions equivalent to 9 to the 4th. So I'm going to start out by writing this, just writing 9 is 3 squared. I know that 9 is 81, so, or 9 squared is 81, so if I take the square root of 81 to the 4th, that should give me this expression. So just kind of starting to think about what might work. So 3 to the 8th, that's what that is, so this would work. 3 to the 6th isn't enough. 9 to the 2nd times 9 to the 2nd is 9 to the 2 plus 2, which would be 9 to the 4th. So C works. D, 9 to the 4th divided by 9 to the 2nd would be 9 to the 4 minus a negative 2, which would be 9 to the 6th. So that does not work. And then 3 to the 4th times 3 to the 4th would be 3 to the 4 plus 4, or 3 to the 8th, which is the same thing as B. So B, C, and E are all expressions equivalent to 9 to the 4th. Now we'll move on to practice set for lesson 3. Select all solutions to m times m times m is equal to 729. So this, if we cubed root each side, we'd get m is equal to the cubed root of 729. So I know that's it. This is square root. That's not right. We can't say that we're just dividing by 3. We're taking a root. Same thing here. This would be false. And these two are equivalent. But 729 to the 1/3 power is a cubed root of 729, so that works. Number 2, in a pond, the area that is covered by algae doubles each week. When the algae was first spotted, the area it covered was about 12.5 square meters. So we want to find the area in square meters covered by algae 10 days. So let's take a look at that. This is each week, and we want to know 10 days after it was spotted. So I'm going to say starting at 12.5 square meters of coverage there, and then it doubles each week, and X is in weeks. So 10 days would be 10 divided by 7 weeks. So I would take this to the 10�7th power, and I think we can just leave it like that. Let's calculate it out here. So we have 12.5 times 2 to the 10�7th power, and we get 33.6465. And this is square meters. And then letter B, explain why we can find the area covered by algae one day after it was spotted by multiplying 12.5 by the 7th root of 2. Well, one day would be, 1/7 of a week. So this would be to the 1/7. Well, we know that anything to the 1/7 power is just that root, the 7th root of that number. So we would have the 7th root of 2 to the 1st power, which is just the 7th root of 2. So you can write it like that. Number 3, the function m is defined by m of h is equal to 300 times 3/4 to the power of h. Represents the amount of medicine in milligrams in a patient's body. H represents the number of hours after the medicine is administered. So what does the m to the 0.5 represent in this situation? This would be the amount of medicine after let's see, this is number of hours, so 1/2 hour later, or after 1/2 hours, yeah. The second one here, letter B, it says this graph represents the function of m, and so we want to use it to estimate the amount left after 1/2 hours. So here's 1/2 hours right here. So I'm going to look at this point here, and I'm going to say approximately 260 milligrams of that medicine is still left in the system then. And suppose the medicine is administered at noon. We want to use the graph to estimate the amount of medicine in the body at 4:30 on the same day. So 4:30, if this was administered at noon, if this is noon here, 0 represents noon, 4.5 would represent 4:30, and we're looking at about 60 milligrams of medicine left in the body at 4:30 then. Did I say 60? Yeah, it's about 80. Sorry. The next one, number 4, the area covered by a lake is 11 square kilometers. It's decreasing, so the lake is shrinking exponentially at a rate of 2% each year and can be modeled by this equation here. By what factor does the area decrease in 10 years? So we could multiply that out, or let's just write it in here. So we'd have 11 times 0.98 raised to the 10th power. And so it would be after 10 years, it would be, if they're just asking by what factor does it decrease, I guess we would just write 0.98 to the 10th, right? That's our multiplier there. And then it asks in letter B, by what factor does the area decrease each month? So now we're talking months, whereas this was 2% each year. And so we would take that 0.98 and raise it to the 1/12th power, which you could write as the 12th root of 0.98. Number 5, the third and fourth numbers in an exponential sequence are 100 and 500. What are the first and second numbers in this sequence? So the third and fourth numbers are 100 and 500, and it's an exponential sequence, and so we're going backwards. We're going to divide by 5 each time. So I'm going to divide by 5 here and get 20, and then I'm going to divide by 5 here and get 4. So the first and second terms in that sequence are 4 and 20. Number 6. The population of a city in thousands is modeled by the function f of t here, 250 times 1.01 raised to the t power, where t is the number of years after 1950. So which of the following are predicted by the model? Select all that apply. So is the population in 1950 was 250? Is that true? No, we're given this in thousands, and so this is not correct. But the next one, B, says the population in 1950 was 250,000, and that's what that would represent there. So letter B is true. The population grows by 1% each year. That looks good to me also. Right there, we're increasing. A 1.01 would be a 1% increase each year. And so this looks good. And let's see, letter D, the population in 1951 was 275,000. Well, let's just multiply 250 times 1.01. And that's, 250. That's 252,500 then if we make it thousands. So this is not true. And the population grows exponentially is true. Anytime we have a growth factor and we keep multiplying to get the next number, that's exponential growth. So that's it for this lesson. I hope this helped. So we'll see you soon.